elastic collisions are a little bit more challenging to solve than inelastic. And this is because two quantities are conserved instead of one, which means you're going to have two equations, and they can ask you to solve for two unknown values. So there's a framework of about 7 steps that you can use to solve any elastic collision problem. So in step 1, you're going to find the initial and final momenta. Step 2, you're going to set the two equal. That's going to be your first quantity. Steps 3 and 4, find the initial and final energies and set those equal. Step 5, you're going to solve the momentum equation, which is 2, for one of the unknowns in terms of the other. You're then going to take that, and in step 6, plug it into the energy equation, solve for the other unknown. And then you're going to take that in step 7 and plug it back into momentum to get them both in terms of things that you do know. Steps 5 through 7 really are just, you solve the system of equations. You have a system of equations, you solve it. So we're going to go through an example so you can see this, because that was kind of just a broad overview. And you can see the nitty-gritty here of what we actually do. So let's say, let's look at an elastic collision. So before the collision happens, I'm going to have a block of mass m traveling to the right with a speed of v. And I'm going to have another block which is at rest, also of mass m. So this velocity is 0. After the collision, I'm going to have the two objects both moving, but they're going to be separate because it's elastic. So I'm going to have m moving with u1 to the right, and I'm also going to have another m, this one, moving to the right with u2. Now the reason I'm having them both moving to the right is the same as in elastic collisions. That's because we want to know if it's moving to the right or left, and the easiest way to do that is if you set them both moving to the right and you solve and get a negative sign, it means that one's actually moving to the left. If you set one of them to the left because you think that's what will happen, and you solve through and get a positive, you're going to have to try to remember, oh, well this positive actually is a negative sign because velocity is a vector, which means it's actually moving the other direction. So the best thing is to always just have them move to the right. Always. And then if one of them is moving to the left, the math and physics will tell you that. So let's go through and solve. Let's find the final speeds of both blocks, final velocities of both objects. So step 1 is to find our initial and final momentum. Well, this has a momentum of mv. This has a momentum of 0. This one is mu1, and this one is mu2. So my initial momentum is going to be the sum of these two blocks, which is just mv. And my final momentum will be the sum of these. So I'm going to have mu1 plus mu2. Step 2, we're going to set them equal. So we're going to have pi equal to pf. So we have mv is equal to mu1 plus mu2. We can simplify this a little bit by canceling out the masses. So we end with v is equal to u1 plus u2. Okay? That's our equation we got from momentum. Step 3, we turn our sights to energy. So the initial energy of this block, I'll write the energy is in green. The initial block will be 1/2 mv squared. This will be 0. This will be 1/2 mu1 squared, and this will be 1/2 mu2 squared. So our initial energy then will be the sum of both the energies of both blocks to start with, which is just 1/2 mv squared. And the final energy will be the sum of the energies of both v's. So you have that the final kinetic energy is equal to 1/2 mu1 squared plus 1/2 mu2 squared. Now we set them equal, and we have 1/2 mv squared is equal to 1/2 mu1 squared plus 1/2 mu2 squared. Now when you're doing this, you do have to be careful, because if you have 3m, for example, for this object, that means you're going to have a 3m here, which is going to be 3/2 mu2 squared. If you have a 2v here, then that 2 also gets squared along with the v, so you're going to have 4/2 mv squared. So you just have to be careful when calculating kinetic energy. So we can simplify this, and we can cancel the m's, we can cancel the halves, and we'll get that v squared is equal to u1 squared plus u2 squared. Now don't be deceived here. This equation may look as though it's the square of this equation, but it's not. because, brief review here, if you want to FOIL two terms, if we want to square both sides of this, v squared is just v squared. You square this, we have u1 plus u2, and we square it. Then we're going to have u1 squared plus 2 u1 u2 plus u2 squared. And that's because you FOIL. Multiply the first terms, the inside terms, outside terms, then the last terms. So you get this kind of interference term in the middle. So they're not the same necessarily. So they're not just the multiple of the other one. So now that we have these two equations, we can go ahead and move on to step 4. Sorry, this was step 4. Setting them equal to step 4. So we can move on to step 5. In step 5, we're going to solve equation 2 for momentum for one of our unknown terms. Let's just do u1. So u1 is equal to v minus u2. And now we're going to take that, and in step 6, we're going to plug it into our equation for energy. So, to kind of split up my work here, we're going to take this, u1, and put it in for our energy. So we have v squared, this is step 6, v squared equals u1 squared plus u2 squared, and we just found that u1 is v minus u2. So, v squared equals, v minus u2 all squared plus u2 squared. Now we're going to FOIL that, so we're going to have v squared, and I'll do this out for those of you who aren't familiar with FOILing. So I'm going to have anything times it's squared is just that term times itself. So v minus u2 times v minus u2 plus u2 squared. So to square this term, we're going to multiply the first term. So I have v squared equals v squared, v times v. Then you add to it this times the last term, which is minus vu2. Then we have this term times this term, so minus vu2 again, then this term times this term. So we get plus u2 squared. Negative times negative is positive. And we still have this plus u2 squared on the outside here. So now we can combine like terms. These v squareds go away. So we have 0 is equal to, well, we have negative 2 vu2 plus 2 u2 squared. So we can divide the whole thing by 2, get rid of that, and I'm left with u2 squared minus v u2 is equal to 0. Now we want to solve for u2, and here you have to be careful. It might be tempting to divide through by u2 and say, oh, u2 equals v. But u2 could also equal 0. That also holds. You can never divide through, when you have something set equal to 0, don't ever divide through by the thing you're trying to solve for if it's multiplying all the terms. Instead, we factor it out. So you have u2 times u2 minus v equals 0. Now, either one of these terms can be equal to 0, and this equation will be true. So really, u2 equals 0, or u2 equals v, right? Because this is from u2 minus v equals 0, so we just solve for u2 there. So which one of these is true? In math, both of these are equally valid. But physically, they're not. What we're doing is this is just calculating the energies and momenta such that energy and momentum are conserved. There's two scenarios where that is true. One of them is where my object at rest is here, my object moving is here, and this one just rolls by the other one because it's in front of it. The second situation where that's true is where they actually collide. So what you need to do is take these two solutions, compare them to what you started with, and then see which one is not the same. So we found object 2 is either 0 or v. Well, object 2 started at 0. So if its speed ends at 0, that means the first object just rolled by it and never hit it. So this is the correct solution, and this is the one we don't want. So now we're on our last step, step 7, where we take this and plug it back into this equation here. Really, we already found u1 in terms of that, so we can say u1 equals v minus u2, and now we know that u2 is v. So we have u1 is equal to v minus v, which is equal to 0. So what happens is the first object slides along, hits the second, stops completely and converts all of its momentum to the other one. You can see this in something called, I think it's called Newton's yo-yo, where these two objects are going to collide elastically. You're going to see this because it's going to look like they're changing color. One of them, these are the same mass, is going to give all of its momentum to the other one, which means this one is going to stop just like this, and this one's going to keep going. It's the end of the day. So you can see this is pretty close to a perfectly elastic collision. It's looking like they're changing color, but really what's happening is the object falling down is stopping, giving all its momentum to the one that's sitting there, and then that just keeps going. So that is how you solve elastic collisions.